and gravity, classical gravity, fit together completely well. There's no problem. So we have a really good description of essentially pretty much almost all the phenomena we see around us. Now, of course, it doesn't describe everything. It has some things that are open questions, and we'll come back to that. But it's a pretty amazing theory. Now, if you think about the different interactions we have here, so everything, so this theory, of course, corresponds to, it's a quantum field theory, and specifically, it's a gauge theory with SU3 course SU2 course U1 broken down to SU2 times U1 electromagnetic. And if we think about the fundamental interactions here, then first of all, we have the electromagnetic interactions mediated by the photon. These, of course, have been known for a very long period of time, and we've gradually developed the understanding of electromagnetic interactions over about 200 years or so. What you know, or what people knew originally, is the static case, electrostatics, magnetostatics, and then you have, of course, electromagnetic waves and their quanta is the photons. But the thing that you knew originally is the classical piece, the electromagnetic waves. Then you have two more instances of the same thing. You have the strong force, the strong interactions in gluons. Only at low energies, these are, of course, confined. And you have the weak interactions with the W and the Z. And these are short-range interactions. Actually, it could be my phone because it does these funny. Okay. So on top of these gauge interactions, we have something completely different, which is the Higgs field. And coming with the Higgs field, we have the Higgs interactions. And I think this is sometimes something that we take too much for granted. So this is something, these interactions are of course mediated by the Higgs field. The Higgs is a spin zero particle. So this is the first time we see such an interaction mediated by a spin zero field. And what we have here are Higgs fermion interactions. So these are the Yukawas. Then we have Higgs interactions with the W and the Z. And of course, we have at the loop level all sorts of induced interactions. So the Higgs interacts with gluons and photons, and these are induced by these fundamental interactions. In this case, too, the thing that we observed first is sort of the classical effects of the Higgs field. So at the classical level, what you see is that the Higgs field gives masses to all the fundamental particles. So, of course, it gives masses to the W, the Z, the top, the bottom, the leptons, and all the other quarks. And so you can say that in the case of the Higgs, what we originally observed was the classical effects of the field. And just 11 years ago or so, we observed the Higgs field itself, which is, again, the quantum of the Higgs field. And this is really something totally revolutionary, because we've never seen such interactions before. They're completely different from everything we've seen up until then. Okay, so that's kind of the framework. If we think about the standard model and this framework of gauge interactions and Higgs interactions, as with anything important in physics, there's usually more than one way or more than one formalism to describe it or to think about it. So the thing that I want to talk about in these lectures is sort of show you or start to discuss a different framework for thinking in particular about gauge interactions and the standard model and beyond the standard model. So the basic ingredient in the standard model is the gauge symmetry, which is a local symmetry of the Lagrangian. But what I want to, one of the things that I want to convey in this set of lectures is that another way to get the same thing, or another way to get gauge theories, is using amplitudes. So what we're going to see is that amplitudes give an alternative formalism or alternative formulation of gauge theories. And since we're also going to talk about massive amplitudes, then there is some hope that we can tie this also to the not just massless gauge theories, but massive gauge theories and the Higgs mechanism. Okay, so you can ask the question, of course, why do we want to think about amplitudes? And I think the first clue that amplitudes can be a good way to go comes from just the calculation of Feynman diagram, just doing calculations using Feynman diagrams for gauge theories. So let's talk about that for a second. So let's talk about QCD calculations. So QCD, of course, is an SU3 gauge theory. And if we're doing perturbative calculations of, let's say, an endpoint gluon amplitude, so I want to calculate some, I want to calculate an amplitude which has n external gluons, then the number of Feynman diagrams that contributes gets big very, very fast. So for n equals 10, there's about 10 million diagrams. But if you look at the sum of these diagrams, if you look at the amplitude itself, the end result is very, very simple. So how simple is it? So this is our endpoint amplitude, and the gluons can have different helicities, of course. If they all have the same helicity, so if it's all plus helicity, or of course all minus, the amplitude is just 0. So you sum lots and lots and lots of Feynman diagrams and you get 0. Similarly, if you have just one minus and the rest are pluses, you also get 0. And the first amplitude that doesn't vanish is the one where you have two minuses, for example, and the rest are pluses. And this guy is non-zero, but you'll see the expression very soon. And it's a very compact expression. It's something that I can write down on half a line. So the fact that, just a second, so the fact that you get so many Feynman diagrams that sum to a very simple result kind of tells you that you're doing something that's not terribly efficient. Yeah.
Is that just like a step to the polarization of the PhD?
The polarization? This is the helicity. These are the helicities of the gluons. And yes, yeah. Excuse me? Color indices? Yeah. Well, I'm not talking about color indices. This is totally orthogonal to the color indices.
Yes.
Yeah.
Is there any way that you can do some systematic study
Yeah.
of color
Yeah.
indices?
So we'll come back to that. But for now, I mean, all I want to say is that for these amplitudes just vanish. I mean, this just vanishes identically, the same for this. And this one I'm writing in a specific, for a specific choice of color ordering. So we'll come back to that.
Is this tree level statement?
Yeah. Thank you. This is tree level. Okay, this is tree level. What's going to happen at the loop level is that these zeros are going to get corrected. Also, the number of Feynman diagrams will proliferate even more. So certainly ask me questions, feel free to interrupt. This way I also will not fall asleep due to jet lag and being after lunch. Okay, good. Yeah. Why? Why do they vanish? Or
Yeah.
That's a very good question.
Yeah.
And although I wasn't planning to address that, but we'll come back to that hopefully. So you can see actually to show that, okay, let's come back to that. Okay.
Yeah.
Right. So, I mean, of course, the point is that with the methods that I'm going to show you, there is a simple way to argue why this should vanish right away. Okay, but the main take-home message that I want you to take from this is that Feynman diagrams are not very efficient. And you can guess right away why they're not efficient. And the reason is the following, that when we work with Lagrangians in Feynman diagrams, we're just not treating the gluon very efficiently. So the gluon, or any other gauge boson for that matter, is a massless spin 1 particle. It has two polarizations or 2 degrees of freedom. But because we want our Lagrangian to be manifestly Lorentz invariant, we need to package this into some Lorentz representation, and the only thing we can use is the 4 vector, right? So here we have, in this vector field, we have 4 degrees of freedom, and so we're just doing something that's not very efficient. So there's a lot of gauge redundancy in this way of doing things. Okay, and so the lesson here is that maybe what we want to do here is we want to focus on the physical degrees of freedom, that is the physical particles. And instead of working with the Lagrangian, work on the scattering amplitude itself, which only cares about the physical particles and sees the physical particles directly. So one thing I want to emphasize is that, it's not like, Lagrangians are very beautiful and gauge theories are very beautiful. But as I said, for important things, there are usually more than one way to think about them. And each way has certain advantages and disadvantages. So this is another approach that we may want to think about. Okay, so the point about amplitudes, the main thing I want to emphasize here is what's called the bootstrap. Bootstrap. So what is the bootstrap? The bootstrap means that you construct amplitudes based on their properties alone. So how does that work? You start from the simplest amplitudes. The simplest amplitudes are 3-point amplitudes. These you can fix by the requirement of Lorentz and other global symmetries. And essentially, that's it. And then you go to higher point amplitudes, that is in larger than 3-point amplitudes. And these you fix from essentially their factorization on lower point amplitudes. Okay, and what does this weird name mean? So bootstrap just means the strap, the little strap that you use to tie your boot. And it refers to, I forget exactly when people started using that, maybe in the late 19th century or something like that, in the US, where in times of hardship, you sort of said that you just need to lift yourself with the straps of your own boots, just like saying that you need to pull yourself out of the swamp with your own hair. So I don't know if you read Baron Munchausen when you were a kid. That's kind of my association of that. So you have to pull yourself with your own hands from some difficult situation. So this is what this refers to. Okay. Yeah. Good question. We'll get there. Okay. Okay. Very good. So let me just give you one example, which I think is a very striking example for what types of things you can see with amplitude. And we're going to work out this example. But for now, let me just tell you what's going to happen. So let's look at the interactions of massless spin 1 particles. And of course, the interactions of spin 1 massless particles are the things that we have at the basis of gauge theories. Okay, so this is sort of where we want to go. So suppose I have spin 1 particles, and the first thing that I can consider is the 3-point coupling or the 3-point amplitude. So here is my amplitude. And these guys have momenta P1, P2, and P3, and they carry some index A. So let me label this. This guy has index A, B, and C. And the thing that we're going to show is that this amplitude, just by Lorentz symmetry, so just by Lorentz symmetry, we're going to show that this has some kinematic factor, which is totally anti-symmetric. And on top of the kinematic structure, what can it have? It can also have some structure that carries the flavor index, or this index, these indices A. So this thing, just by Lorentz, is going to be completely anti-symmetric. That is, it's anti-symmetric under the exchange of 1, 2, 1, 3, 2, 3. And so because the whole amplitude has to be symmetric under the exchange of these guys, because they're bosons, this thing also needs to be totally anti-symmetric. So what does this remind you of? Structure constants. Okay, so the fact that it's completely anti-symmetric tells you that, I don't know if this is what it is, but at least it has, it's consistent with being the structure constant. Yeah.
So what is clear is that you can decompose the kinematic term and the totally symmetrical.
Yeah.
Yeah.
So you want to know why I can sort of factor it in this way. Yeah.
Is there any theorem or just
It's not a theorem, but when we'll construct it explicitly, you'll see that
just
it's really not, because there's only one term that's sitting here essentially. So it's got to be multiplied by something. It's not like I have a bunch of terms that I can write down.
I see. Yeah.
Okay.
Yeah.
Okay, so we look at the 3-point couplings and we see a structure that's totally anti-symmetric. So that's kind of promising. And now we go to the 4-point amplitude. So now this is some 4-point amplitude. And now the thing that we'll see from this is that we have C, A, B, E, C, C, D, E plus permutations equal to 0. So what this is, it's the Jacobi identity. So that's it. I mean, once we have this, what we get is the full classification of Lie algebras. Because what you probably learned in QFT about Lie algebras is that the generators satisfy, so we have generators that satisfy I, F, A, B, C, TC. So what defines, first of all, the algebra is these structure constants. They're totally anti-symmetric. They satisfy the Jacobi identity. And from that, you can classify the full list of Lie groups. And I think that's totally amazing because, you know, I think there's a quote that I heard once that I don't quite remember, that Lie was super happy when he found Lie algebras. And he said, this is something that physicists will never use. Okay, they'll never lay their hands on. But in this case, you see that just the consistent interactions of spin 1 mesos particles gives you this full structure of Lie algebras. And actually what we're going to see is that it's not just massless particles. I can also talk about massive particles, and I'm going to get exactly the same thing. So this is kind of the spirit of what we're going to do, and we're going to work that out explicitly. Okay. Okay, so I want to go back to our motivation, which was, we said I want to ultimately apply this to thinking about beyond the standard model. So when we talk about BSM, there are of course many open questions. Some of these questions are more empirical, and some of these questions are more theoretical. And I'm not going to repeat the usual list, but of course, there's dark matter, which is the big elephant in the room. There's the matter, antimatter asymmetry. There are other things, but the thing I want to sort of focus on is the Higgs mechanism. So we have this very nice picture where we have the Higgs being an SU2 doublet. And in this SU2 doublet, we have a VEV here, and then there's the physical Higgs, and then there's a goldstone here, and another goldstone here. And everything works beautifully. But in order to get this Higgs mechanism, we really need to have this VEV here. And we have absolutely no understanding of that. So what do? We just do what we need to do. We write something by hand. We write a Higgs potential, which is this thing, which gives you the Mexican hat and gives you symmetry breaking and so on and so forth. But this is a completely effective description. It's completely ad hoc. Okay? There's no explanation for why we have this mu squared, which is negative. We have no understanding of why mu is around 100 GeV. And finally, we have no explanation for what stabilizes mu. And this is, of course, this goes under the name of naturalness or fine-tuning or the hierarchy problem. So all these things have absolutely no explanation. And it's just something that we write as an effective description. And so it would be really nice if we had some BSM theory that describes that. And the other thing that's really nice is that we have the LHC. So, and the LHC probes energies that we've never seen before. So if you think about, what's the place where you're most likely to find new physics, of course, you're not guaranteed, but it's the LHC. And there's a hope that if we really look closely at things that, at LHC experiments, we'll have a clue about this new physics. Now, one thing that I want to stress is that there are BSM scenarios that do all of these things, okay, and do this very beautifully. So I'm not going to enter into any detail, but personally, I think the most compelling one is supersymmetry with supersymmetry break-in that's dynamical. So in this case, you have many things that happen. First of all, starting with some superpartner masses at the high scale, you run down to low energies and you find that the negative mu squared just occurs. And so you have a reason for why you have this Mexican head potential. It's very natural to arrange for scales like this because you have some dynamical sector that breaks supersymmetry. So you have a scale that's hierarchically smaller than the Planck scale. And finally, you have supersymmetry that stabilizes this value, the Higgs mass. So you have concrete models in which all of these things can happen. But at this point, we just don't know whether any of them are at play. Okay. Okay, so the thing, as I said before, the thing that I want to emphasize with amplitudes is that we have a different way of thinking about gauge theories. We have a different way of thinking about the Higgs mechanism. And so this is something that may be utilized in order to probe for physics beyond the standard model. Now, don't get me wrong. I'm not saying that I have any alternative explanations of naturalness or solutions to naturalness. This is not meant to be an alternative to that. But it's just another way to formulate things. And the fact is, we really don't know what's generating this. We don't know whether the standard model is the full story. We know that there are many things that we don't know. We know that the gauge theories are not very economical. And so it makes sense to stick to the physical degrees of freedom and see what we can get from that. Okay. So we'll need to go through the basics of amplitudes. And what I will start to do today, and it's going to be quite a lot of work, is we're going to describe spinor variables. We'll do the massless and the massive case sort of together. Then we'll talk about factorization. And then we'll talk about the bootstrap. And so this is the plan for the first part of these lectures. Okay, so let's start on that.
Distinguish whether the statement is only holds for tree level or loop level, but it sounds like it's still not completely independent from the Feynman diagram picture. So isn't it?
No, there are many things you can do completely without Feynman diagrams.
So does it mean that it holds even, is there, but you still talk about the loop and tree level, whatever. So is it still independent from the Feynman diagram?
Yeah, there are many things that you can do independently of Feynman diagrams. I'm not going to claim that you can reproduce all the results of QFT in this way, but many you can reproduce.
Okay.
Okay. Okay. So my conventions are the following. So fortunately, I'm going to use the same metric as Rocky does. So this is the West Coast metric. I'm going to mostly follow the conventions of Peskin and Schroeder. And I just want to remind you from that book that you have the Pauli matrices, sigma mu, or the generalized Pauli matrices. So sigma mu is these guys, and sigma bar mu is these guys. And I think this is pretty much what we're going to do, what we're going to need from conventions. And as I said before, as I wrote here, I'm using the conventions in my papers from 2018 and 2019. Okay, so let's start talking about amplitudes. And let's start with the basics. Okay, so suppose we have a scattering process. If you think about it, almost any physical observable that you're familiar with is related to some scattering process, either a scattering amplitude or a decay or transition amplitude, which is a special case of that. So I can think of this as two particles going into n minus 2 particles. So altogether, I have n particles in my amplitude. And this is described by the S matrix. And the S matrix can be written as 1 plus IT, where the 1 says that nothing happens. There's no scattering. The final state is the same as the initial state. And this guy here is the transition matrix or transition operator. And the scattering amplitude is, of course, the matrix element of this guy. So if we look at P1 to PF, IT, K1, K2, this is equal to 2 pi to the 4 delta 4 of K1 plus K2 minus sum over P J times IA of K1, K2 to P1 to PF. And at the end of the day, what we want to do is we want to calculate a cross-section. In the cross-section, the sigma is related to the amplitude absolute value squared. So there's some kinematic factor here. We have the phase space, D3PJ over 2 pi cubed. And finally, 1 over 2 EJ. And then we have A squared times the delta function for momentum conservation. So the cross-section is related to the amplitude absolute value squared. And one last thing that I want to mention about the S matrix, and this is going to be super important in the following, is the optical theorem. So we know that the S matrix is unitary. So that means S dagger S equals 1. And that tells you that the imaginary of t is equal to 1/2 t dagger t. And so it relates the imaginary cuts of this t to the square of t. Okay, so we'll come back to this. Okay, now I'm sure you all learned in QFT how to calculate amplitude. So let me quickly remind you of that. Okay, so what you learned in QFT. Let's start with the scalar theory. Suppose I want to calculate an endpoint amplitude. So what should I do? I should look at the correlator, the endpoint correlator, phi x1 to phi xn. I should go to momentum space. And there, if I'm interested in the amplitude, I should look for the multi-particle pole such that I have a pole for each one of the external legs. So each one of the external legs comes with something like this. And the residue of that, okay, taking out this piece, the residue of that is our amplitude. Okay, so the amplitude is the residue of this multi-particle pole up to the factors of z here. And therefore, what it's given by is it's given by the sum over amputated Feynman diagrams, meaning that there's no propagator for any of the external legs. So this is something I'm sure you're all familiar with. And let me just remind you that when we write this type of thing, what we have in mind is that we're working in the complex plane for the momenta, right? We're analytically continuing to the complex plane. So pretty soon we're going to take the momenta to be completely complex, but you shouldn't be too surprised by that because it's something that you've been doing forever and ever. Okay, so that's just a reminder of that. And this was for scalar particles. So now let's go on and talk about particles with spin. Spinning particles. So when we're talking about particles with spins, what we need to do in order to specify the particle is two directions in principle, or three vectors. So one, of course, is the momentum, and the other one is the spin quantization axis. This is the direction along which we define our spin. If we're talking about massless particles, then it's very natural to work with helicity states. And then this n is equal to p. So we just have a single direction. But for anything else, and in particular for massive particles, we need two directions. So that's one thing to keep in mind. There are two, the spin can be either up or down. But what I mean is that I'm asking the question, how many directions do I need in order to describe the particle?
Yeah.
Okay, so it's the axis.
Yeah. Since
Okay.
you write down the equal sign for the n hat and p hat.
Yes, yes.
Yeah, so
right.
I thought
But
like that.
Because my n is not the direction of the spin, it's the spin axis. It's the direction along which I define the spin.
Oh,
And it
okay.
can be either up or down,
Yeah,
or
then you,
whatever. along the
you
direction.
mean just for massless particle, the particle has only two helicity state.
Right.
Yeah, yeah.
But it's the axis.
Yeah, momentum axis. Okay, thank you.
Okay. Um, so, um, so for the case of spinning particles, the amplitude, of course, contains the polarizations. And these polarizations contain the spin information. And essentially what the polarizations do is they project from the field to the particle, to the physical particle. So you're used to this for spin 1/2 particles. You have an amplitude. This is my external leg P, and it has to come with a USP or U bar SP or VSP or V bar SP, depending on whether this is an incoming fermion, an outgoing fermion, and similarly for antifermions. And this S takes the values 1 and 2, which is the right thing because we can have two spin states, up and down. Similarly, for vector fields, for spin 1 particles, for this external leg, I need to include some epsilon I of P. And this I runs over 1 and 2 for massless particles, and it runs over 1, 2, and 3 for massive particles. So these are things that you know very well. And essentially what we're going to do today is to learn how to write all these things in terms of massless spinors. Okay, so let me remind you what all these polarizations are. And then we can rewrite them all in terms of massless spinors. So let's talk first of all about the fermion polarizations. That is the U of P. So U, of course, solves the Dirac equation, sort of the solution of the Dirac equation, P slash minus M UP equals 0. And you know the two solutions. I can write them as follows. I can write them like this. Where S equals 1 and 2 describes the two spin states. This is exactly the form that Peskin uses. And I think you probably saw that before. For example, suppose my particle, or suppose I choose the z-axis along the particle direction. So P equals the 3 direction. Then I could choose my two X's to be 1, 0 and 0, 1. And these essentially give the helicity states. So U of P in this case is equal to square root E minus P times 1, 0, and square root E plus P 0, 1 for one state. And if I look at m equals 0, you see that it just reduces to this guy here. So we have a state of specific chirality. Okay, so these are all things that you know. Similarly, you know how to choose your vector polarizations. So suppose I have a vector of momentum k, and I need to include the polarization epsilon k. So what characterizes this epsilon k is that k dot epsilon equals 0, and we can choose to normalize it such that epsilon dot epsilon star equals -1. That's the standard normalization. And if we take m equals 0 and choose again z to be in the k direction, then our k is E 0, 0, E. And we can choose epsilon to be 1 over square root of 2, 0, minus plus 1, minus I 0. So this is for the plus or minus polarizations. And that's the choice that we usually make. But of course, we could take epsilon to be epsilon plus any number times k. And that guy is a totally fine polarization because it satisfies, it still satisfies this and this, and it's not going to make any difference to our amplitude because of the word identity, right? So because of the gauge invariance or the word identity, either one of these guys works. And this is precisely the gauge freedom that you have manifested in the amplitude. Now, if we instead talk about emissive polarization, so suppose we now have M that is non-zero. Then in addition to these two polarizations that we wrote over there, we also have a longitudinal polarization, which is the following: epsilon mu of k, z, and this is the zero label is k over m, 0, 0, e over m. And you see that this does depend on the magnitude of the momentum itself. Unlike the previous one that doesn't care about the magnitude, it only cares about its direction. And okay, so that's the end of the story. At this point, we know how to write down polarizations for spin 1/2 fermions, for spin 1 particles, and we can write A, the amplitude, in terms of the momenta and polarizations. And it's here that the spinor information is residing. Okay. So let me now give you a very brief review of what we need to know about the Lorentz group, or the Lorentz algebra. So you know that the Lorentz algebra is given by SO3, 1, and it's isomorphic to SU2 times SU2, which we can call SU2 left times SU2 right. And if you don't remember that, then Peskin has this great problem, 3.1, that you should work out. because it's super useful. And there what you do is you remember that the Lorentz generators or the Lorentz algebra is this. It's this terrible mess here. G mu rho J mu sigma minus and plus other things. And then we can take combinations of the Lorentz generators. We can define the LIs, which is 1/2 epsilon I jk j jk. These guys give rotations. And then we have the KIs, which are J0I. These are the boosts. And out of these guys, and each one of these guys, or out of these guys, we can form other combinations. So we can form J pluses that are 1/2 L plus IK, and J minuses, which are these guys, and J pluses form one SU2, and the J minuses form the other SU2. And we can classify the representations of Lorentz as the doublet representations of this SU2 and this SU2. And these are the basic building blocks that you can use to form all the other representations of Lorentz. Okay. So now what we want to do is we want to take this amplitude and we basically want to rewrite it completely in terms of massless spinors that transform under this representation and this representation. So let's see how to do that. Okay, so again, let me remind you, we talked about these spinners. So we had this Dirac spinner that we wrote down before, psi x. We can write this guy as psi L of x, psi R of x, where these are, both of these are two-component spinners, and they transform under these two different SU2s. So under a Lorentz transformation, psi L goes to 1 minus I theta plus beta dot sigma over 2, and psi R goes to 1 minus I theta minus beta dot sigma over 2. This is psi L, this is psi R. Here you can identify, essentially, you can write this as minus I sum alpha L dot JL. And here you have minus I beta L dot JR. Okay, so these transform under the SU2 left and the SU2 right. And the Dirac equation connects them. It connects them in the following way. We have minus M I sigma dot D I sigma bar dot D minus M psi L psi R equals 0. Okay, and now this is essentially all we need. What we're going to use all the time is these two spinners, psi L and psi R, but we're just going to change notation because it's a little more convenient. So let's introduce this notation. But this is really nothing but notation at this point. So we're going to use two component spinners. And we're going to label them as follows. So the SU2L indices we're sometimes going to call alpha, where alpha runs over 1 and 2. And the SU2R indices we're going to call alpha dot, that runs over 1 and 2. And then the spinners we're going to denote by either lambda alpha over here or a ket like this. And these are two redundant notations. Like we can use either this or that, but people use both of them, so we introduce both of them. And similarly here, we use lambda tilde alpha dot, or we sometimes denote it with a square like this.
In this case, the alpha means helicity over massive spin particle.
In this case, at this point, it doesn't mean anything. It's just a mathematical thing, okay? It just labels my, I'm talking about two SU2 representations. I'm saying that I call the indices of this SU2 left by alphas and the indices of this SU2R by alpha dot. But it corresponds, at the end of the day, it's going for massless spinners. It will correspond to helicity states. Okay.
Since if we consider massive case, then we have also
both of them. Right. 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 Now, first of all, so sometimes we refer to these as chiralities, right? So this is one. These are positive chirality and negative chirality indices, and in the massless case, they correspond to helicity. Right. Okay. Now we can lower and raise the indices with the anti-symmetric tensor. So we use epsilon alpha beta or epsilon alpha dot beta dot to raise and lower the indices. So this is the Levi-Civita tensor in 2D. So it's completely anti-symmetric. And my convention is going to be that epsilon 1, 2 equals 1, and epsilon ij is, of course, minus epsilon ji, and is minus epsilon ij. And so now we can define contractions of these two component spinners. Yeah. No, it's okay.
Is there any reason to use the polygon and square bracket?
Yeah. So you want to know
Yeah.
why we contract indices in this way or another?
Yes.
It's a consistent way to work, okay, which
Yeah.
is good. I mean, there are, of course, many different different people use different conventions, so you have to be very careful.
Yes.
There's an excellent review on two component spinners by Haber, Martin, and Drainer. So I really recommend that. This is like the Bible of two component spinners. It's a very big,
Yeah.
they also convert from some notations to another.
Actually, what I want to ask you exactly is there any physical reason to use for the SU2L we use the curly bracket? No.
No, I don't think so. No.
Oh, okay,
No.
I see.
I mean, you could use any convention that works. It should all be the same. Yeah. Okay. So we can define these contractions, lambda chi, which I'm going to define as epsilon alpha beta, lambda alpha chi beta, which is which can be denoted as lambda alpha chi alpha, and this is minus chi lambda. So that's the thing I want you to notice is that this product is anti-symmetric. And similarly, we can define these guys. And these are defined as epsilon alpha dot beta dot, lambda alpha dot, lambda beta dot, chi beta dot. And this is equal to, so this is going to be the same as lambda alpha dot chi alpha dot. And this is minus chi lambda. Okay, and so the thing to note here is that, of course, lambda lambda and lambda tilde both vanish. Okay, so these guys, these spinor products, this guy is called the, we're going to call that obviously the angle bracket, and this is just the bracket. These are going to be the basic things with which we'll write the amplitudes. Okay. Okay, so as with anything, so we already said that we can write the amplitude in terms of momenta and u's and v's and epsilons. And as always, there are many ways to write it. We can also write the whole thing in terms of massless spinor products. There are other things that people use, like twisters and momentum twisters and other things, but each one of these things has certain advantages. The nice thing about what we'll do here is that all the amplitudes have sort of a uniform representation. Like we write all the amplitudes independently of the spin in terms of these massless spinor products. And the other thing that's nice about this is that the little group properties of the amplitudes are going to be manifest. And it will allow us to derive all sorts of selection rules on the amplitudes right away. Okay, so let's continue with this. Okay, so let's first of all talk about massless things. And for massless things, remember we need to write spinors, momenta, and vector polarization in terms of massless spinors. For spinors, it's kind of trivial. I mean, the spinors that we use are lambda p 0. So I can write this like this. I can just label it with P. And of course, this thing satisfies P mu, sigma mu equals 0, which we can write as P equals 0. So when I just write P, I mean that P mu is contracted with either sigma or sigma bar as appropriate. And this is one type of spinor that we have. And then we also have this guy. So this guy, we're going to label like this. And this guy satisfies that P mu sigma bar mu P equals 0. And again, I can write this just as PP equals 0. Yeah.
The low case, the momentum P is open to the sigma bar. Then in order to distinguish with the overall, we need to include another symbol.
I can, but I'm not going to do that.
Okay.
Okay. So yeah. And, you know, if I try to do that, I would get it randomly incorrect. But that's just what it needs to be. Yeah, but you're right. Okay, so that's the first thing we need. Spinors are easy. Then the second thing that we want to do is we want to write momenta in terms of spinors. So let's do that. So you kind of, you're used to that. In any QFT class, what you usually do is you do sum over polarizations, U bar equals P slash minus M. So this is now just the massless case. You can write P slash in terms of massless spinors. This is exactly what we do here. So let's see how it works. So essentially, instead of P, I can work with P mu gamma mu, which is 0 P mu sigma mu alpha beta dot P mu sigma bar mu alpha dot beta and 0. And if you write that explicitly, you see that P mu sigma mu is equal to the following thing. It's P0 plus P3, P1 minus IP2, P1 plus IP2, P0 minus P3. And if you calculate the determinant of this thing, it gives 0. This is just a simple thing to do. In the massless case, you just get P0 squared minus P3 squared minus P1 squared minus P2 squared, which is 0. So you see that you can write it in terms of a single two-component vector, or otherwise a single two-component spinor. So we can write P alpha alpha dot is lambda alpha cross lambda alpha dot, or we can write that as P times P, using the notation that I introduced before. So I can write my momentum or any light-like vector in terms of a single spinor. Okay. Now, one thing that I forgot to tell you before, and this is important, is that for real momenta, or this is a good time to tell you, for real momenta, P star is equal to this guy. So the complex conjugate just exchanges the square and the angle. Okay, so at this point, we know how to write fermion polarizations, we know how to write momenta, and now the other thing we need to do is we need to write the vector polarization. Yeah.
I think the bracket notation is represents kind of two component vector, and I think we need to use dagger. Yeah.
No, it's okay like that. In my conventions, it's fine. Let's talk about it later, but this is fine.
Since we will use the index notation.
We're never going to use indices, really. I mean, we're mostly going to use this notation. But this is okay as is. Okay. Okay, so that was the second thing we needed, is how to write momenta. And now let me write vector polarizations. So again, let's say that our K mu is K1001. that is, we choose the z-axis along the momentum. So we said before that epsilon mu of z and plus or minus 1 is equal to 1 over square root of 2, 0 plus minus 1, I 0. And now I want to write this in a covariant form. So I don't want to have to write this completely independent vector for each k mu that I have. So to write it in a covariant form, what we can do is we can introduce a 4 vector, k tilde, which is equal to k 0, 0 minus k. And then we can write our epsilon mu of k and plus minus 1 is in the following form. We can write it as 1 over square root of 2, k minus plus sigma mu or sigma bar mu, depending on which one you have here, k tilde plus minus, divided by k plus minus k tilde minus plus, corresponding to negative or positive spinors. And so let me write it in the notation that I introduced above. So in the notation that I introduced above, epsilon mu of k plus 1, for example, is equal to minus 1 over square root of 2, k sigma mu k tilde divided by k tilde. Now this is not going to be the final form that we're going to use, because we'll do another step. So here I chose a specific k tilde and I wrote the usual polarization in this way. But remember that this is kind of arbitrary. I can take epsilon mu and change it to epsilon mu plus some number times k mu. So actually, instead of working with this k, vector, we can replace it by any arbitrary vector r. So this r is some arbitrary light-like momentum. And we can write our polarizations in the following form. So epsilon plus alpha dot of k is going to be equal to square root of 2 r k divided by kr, and epsilon minus alpha dot is equal to square root of 2 k r divided by kr. And what you can check, and this is a good exercise, you can check that this is really correct. That is, if I go from the form that I have up there to having any arbitrary r here, it just corresponds to changing epsilon by something proportional to k mu. So now we have nice expressions for the polarization vectors. We wrote them in terms of two-component spinors, these massless two-component spinors. They depend on an arbitrary vector r, but that shouldn't be too surprising because we have the gauge freedom in the game, right? So the word identity is going to guarantee that things don't, that this r doesn't matter here. any R dependence should go away. Yeah. That's exactly that's the gauge freedom. The gauge freedom basically amounts to changing these R's here. Yeah. Okay. And so at this point, we have what we promised. For the massless case, we have the amplitude in terms of, we have all of these guys in terms of massless spinors. So the amplitude as a whole is going to be given by massless spinor products. Okay. So let me just say this, and I guess we'll have to end here. So once we write everything in terms of these massless spinors, the amplitude A will be given in terms of massless spinor products. So these are going to be something like Pi, Pj, which we can abbreviate as Ij, or Pi, Pj, which we can abbreviate as Ij. And remember that II is 0, and similarly II is 0. As long as we talk about real momenta, then Ij star is Ji. And there is one other thing that's useful to bear in mind. So suppose that we calculate 2pi dot pj. Why am I interested in this? Because, I mean, if my pi and pj squared are 0, then pi plus pj squared is 2pi dot pj. This is the thing that we often call Sij, the Mandelstam Ij. And then I can write this in the following form. I can write this as Pi alpha alpha dot Pj alpha dot alpha, which I can write as the trace of Pi, Pj, Pj. And what I used here is the fact that sigma mu alpha alpha dot sigma mu beta dot beta is equal to 2 delta alpha beta delta alpha dot beta dot. So now, since this is a trace, this is equal to the trace of Pi Pj times Pj Pi. And then I just get, so this is the thing that we called Ij Ji. I got my indices wrong here. And I'm possibly missing a factor of 2 because this is a trace over a 2-component thing. So let me leave the factor of 2 to you. And anyway, the end of the story is that I can write Sij is ij times ji. So this is something that will be useful as we go on. And let me just say one more thing. So you see that if you have real momenta, then each one of these spinor products is just given by the square root of Sij up to some phase. And this guy is minus square root Sij into the minus I phi. Okay, so these things are just numbers, okay? It's just a complex number. The absolute value is equal to the square root of Sij up to some phase. Okay, so I'm afraid we have to stop here, and we'll have to go on with this tomorrow. It's on the polarizations and the momenta, and we learned how to write all of that in terms of two-component spinors that we denoted by these square and angles. And what we're going to do today is to, first of all, continue this to non-zero masses. Then we're going to start on 3 points and essentially classify all the massless 3 points, and then go on to discuss 4 points. And this is how we're going to see the Jacobi identity arise. So this is kind of the plan. We'll see how far we get. But one little thing that I still need to complete regarding the two-component spinors that we discussed is something very useful that's called the Schouten identity. And the statement is very simple. If you think about these two-component spinors, it has two components. So we can span it in terms of two independent spinors. So I can write it as some constant times j plus some constant times k for some independent spinors j and k, where these a and b are just complex numbers. And now if we take the product of this with I, for example, with let me take j here. So this guy is gonna drop out, and I get to be here times jk, and so that fixes b is ji over jk. Similarly, you can do the same thing to determine a, and then you can take the product of this with some spinor L, and then we get the identity, which says that Li jk plus L jki plus L kij, this whole thing vanishes. And the same thing for the square spinors. So we have these identities that the spinors satisfy. So this is one thing that is useful when you do manipulations with these 2D spinors. Okay, so now I want to start talking about massive amplitude. And again, what we'll need to do is repeat the story that we had yesterday. We want to know how to write the polarizations and the momenta of massive particles in terms of massless spinors. So let's start with the momenta. So now we have some momentum p, but p squared equals m squared. But we can always write such a momentum in terms of a sum k plus q, where these two guys are light-like. The one thing that these guys need to satisfy is they need to satisfy that 2k dot q equals p squared. So that's equal to m squared. And notice that the only thing that we need to choose here is the direction k. Because once I chose the direction k, then q is fixed, and then, or q is fixed, let's say q is fixed, and then I can also determine the magnitudes by this relation here. Okay, so this is exactly what can be expected because this is a massive momentum. This is a massive particle. We see that there's another direction that we need to invoke here, which is this k hat. And that's going to be exactly the thing that we need in order to describe the spin axis of this massive particle. Okay, so once we've done that, we're done because now we have P written in terms of two light-like momenta. And each one of them we can write in terms of massless spinners, just like we did yesterday. Okay, only in this case, in the massless case, we needed one spinner. As long as we're talking about real momenta, we needed one spinner to describe the momentum. Here we have two light-like momenta, so we'll need two spinners, two independent spinners. So once we do that, we can replace the momentum P by two independent spinners. Now let's introduce a little bit of more notation. So instead of calling these guys K and Q, let me write it as, let's give them an index I, where this index I takes the values 1 and 2. And now I can write P alpha alpha dot, for example, is just the sum of the of this guy plus this guy written in terms of two component spinners. So this is going to be epsilon ij lambda alpha I lambda tilde alpha dot j. And we can also write it as P I Pj, Pi Pi, using the notations that we had yesterday. So I'm doing exactly the same thing, only now I have a sum over I here, where I runs over 1 and 2. Okay? Good. So we know what to do with momenta. Now let's talk about polarizations. So let me start with fermions. So for spin 1/2 fermions, we can write our Dirac spinners in terms of these guys. So I can write them again either in terms of lambdas or in terms of angle and square spinners like we did before. So this will be Pi, and this is going to be Pi. And you can easily check that this indeed satisfies the Dirac equation. So that's an easy exercise that you can do. Okay, so that's easy. One thing that I want you to notice is that if we look at something like P1, P2, for example, then remember that P1, P2 times P2, P1 equals 2 P1 dot P2. And that was our m squared. So for real momenta, each one of these guys is equal to m up to a phase. Okay, so this is equal to m times some e to the I phi, and this guy is equal to m times e to the minus I phi. And we can choose, for example, phi equals 0, such that each one of these is equal to m. Okay, then the last thing we need is the polarizations for spin 1 particles. And I already wrote down for you the polarizations for the massive spin 1 particles. So all I want to do now is to rewrite them in terms of this new notation. And I'll just give you the results because this is completely straightforward. Again, it's something that you can check, but there's nothing too interesting going on here. So epsilon mu plus we can write as P1 sigma mu P1 divided by square root of 2m. Epsilon mu minus we can write as P2 sigma mu P2 over square root of 2m. And epsilon mu 0 we can write as 1 over 2m times P1 sigma mu P2. And that's it, plus the same thing with 1 and 2 exchanged. So I can also write these guys down in terms of, because here I have the index 1 appearing twice, I can also write this as epsilon 1, 1. This guy is epsilon 2, 2. And this guy is epsilon 1, 2. But the 1 and 2 are symmetrized. So let's indicate that explicitly. And so collectively, we can write all of these polarizations together. So our polarization is now this tensor epsilon mu ij, as we wrote over there. And I can write it collectively as square root of 2 pi I pj and I need an m here. And these indices are symmetrized. So in order to not have to write these indices again and again, we can introduce some notation. And this is actually a notation that was introduced in this 2017 paper by Arkani Hamid and company, where instead of writing these indices explicitly, they just bolded these momenta. So I can write it also like this, where these two momenta, these two spinners should be bolded. Now, of course, it's I'm not gonna bold spinners for you on the board, or we'll never finish these lectures. So instead, I'm gonna use underline. So I'm just gonna write it like this, P and P. This is gonna, these underlined momenta or these underlined spinners are going to stand for bolded spinners. But what this stands for is just keeping these I and J indices implicit, and implicitly you symmetrize over them. Okay, and the same thing is going to hold for the for these guys. So for fermions, I also have to write down things that carry an index I. So again, I'm gonna underline them, and that means that there is an implicit index I that's hiding there. And in this case, there's only one of them, so there's no symmetrization. Okay, so at this point, we're basically done. We know how to write massive momenta and polarizations in terms of massless spinors. And this is not, as we said before, this isn't too surprising because we know that any SU2 representation we can form by taking a number of doublets in symmetric combinations. Because, you know, if we take two doublets in an anti-symmetric combination, we get a singlet. So that doesn't give us anything interesting. Okay. So the rules are now very simple. But before we talk about the rules, let me say something else. So let's go back to our expressions for the momenta. So for the momenta, we say that for an m equals 0 momentum, we can write the momentum as pp. And for massive momenta, we can write p as pi pi. Okay. And so you see that in either case, we still have some freedom that's left in defining our spinors. So for example, in this case, we can take p to e to the I theta p. We can phase rotate it. And similarly, and then we of course need to take p to e to the minus I theta p. And the momentum stays invariant. So here we have some U1 freedom to change the, to redefine our spinors. Here we have an SU2 freedom, right? Because I can take PI to some matrix Wij P and do the opposite thing for P. So I want to take P to W dagger P, as long as W dagger W equals 1. So this is acting in two-dimensional space. So here we have an SU2 freedom. So we can redefine our spinors by SU2 matrices in this case, by U1 transformations in this case, and the momentum stays the same. And of course, you recognize this immediately as the little group transformations. So the little group transformations are the subgroup of Lorentz transformations that leave the momentum invariant. And what we get here is precisely the correct thing. So if you think about, let's start with the massive case. So with the massive case, the easiest way to see the little group is to go to the rest frame. So in the rest frame, the momentum is m and a 3-vector 0. And I can rotate this 3-vector any way I want, and the momentum is going to stay the same. So here the little group is SO3, which is isomorphic to SU2. And for m equals 0, I can write my momentum as 1, 0, 0, 1. And then I can rotate between these two guys, which is an SO2. And that's like a U1. So the freedom that we see over there, the freedom to redefine the spinners or rotate the spinners is exactly the little group transformations. And so that's going to be a key element in everything we're going to do. Okay, so why does this help us? It helps us because this is like, this is sort of telling us what is the charge of the amplitude under the little group. Okay, so the thing that we know is the following. We know that for each external spin 1/2 leg, the amplitude needs to carry, so first let's talk about m equals 0. So if this fermion leg has plus helicity, let's call it h equals plus 1/2, then this leg comes with a factor of p angle. If h equals to minus 1/2, it comes with a square. And similarly, for massive guys, we can have either p or p. And of course, in this case, helicity is not a good quantum number. We don't have conserved helicity, and we can, acting with p, we can change from this guy to this guy. So, but the only thing that we know is that for each massive spin 1/2 leg, the amplitude needs to carry this factor or this factor. Then for spin 1 particles, it's exactly double that. So for each spin 1 leg, if m equals 0, if our h equals plus 1, then we need 2 of these guys. If h equals minus 1, we have 2 of these guys. And for massive guys, we can have either this or this or two angles. Okay, and of course, if we have a scalar leg, then it doesn't come with any polarization, so it doesn't come with any of these factors. Okay, so that essentially tells us that the amplitude carries some charge under the little group. In this case, for example, I can take p to e to the I theta p, as we said before. So this is like, I can say that this here I'm assigning weight or charge equals plus 1. Actually, I see that I switch my notations. So this will be my plus, my minus, and this will be my plus. And so this is charge plus 1 or weight plus 1 under the little group. I can think of this as the little group weight plus 1. Well, I said minus 1 here, plus 1 here. And in this case, the amplitude transforms as a doublet of the little group. It carries either this guy or this guy. And similarly for the vectors, again, we have the amplitude has to carry charge plus 2 or minus 2, or have these two doublets in a symmetric combination. So this is going to give us selection rules on the allowed amplitudes, and specifically little group selection rules. Any questions about this? Okay. Weight is like a charge, okay? Instead of, in the case of the U1, I can just talk about a U1 charge. It's a regular additive charge, or I can talk about a weight. And here again, it's kind of a charge, but it's a non-abelian charge. It's just the representation. Okay, good. So we've been writing all these meshless spinners, and they may seem very mysterious, but I just want to give you an explicit form for these spinners, which is not unique, of course, but just so you see that there's nothing mysterious about them. So suppose our momentum is this, the usual thing, sine theta, cosine phi here, p, sine theta, sine phi p, and p cosine theta. And, oh, sorry, I actually wanted to write a massless guy, of course. Okay, so this is what I want to write. So in this case, I can choose my spinners to be as follows. So P is e to the I alpha square root of P0 minus P3, P1 minus IP2, P0 minus P3. And I see that I didn't I didn't actually substitute the different values for this, but you can just substitute them yourselves. And you'll notice that when E much bigger than M, we can write this as e to the I alpha squared to E sine theta over 2 sine theta over 2 e to the minus I phi over 2. And this alpha is an arbitrary phase. So you can, for each momentum, you can just stick in the different components and you'll get some explicit form for the spinners. Yeah. I think you're probably right, and that's probably a typo in my notes. Thank you. So according to Rocky's rule, that's 1/3 of the homework assignment credit, right? I'll go with the 3. Okay, very good. So I'm not going to write the square spinner because you can just find it in the notes and correct. Well, there I didn't write the explicit form. Okay. Okay, very good. So I was going to do an explicit example just to get some practice with working with these spinners. But instead, I'm going to leave it as homework to you. Unless, of course, you already did it last night because you already had the notes. So I'm sure this is what you went to do last night. So I want to do the example of Compton scattering. Namely, E gamma going to E gamma using these using this new notation of massless spinners. So this is fully massless. Everything is going to be fully massless here. And I'm not going to do it. It's in the notes, but I want you to actually go through it. And this is going to be the homework. And we can discuss it in the discussion session today. It's very easy, so shouldn't take that long. Okay, so but let me just give you some guidelines. So essentially, what I want to do, instead of talking about this amplitude, I want to use crossing symmetry and treat everything as incoming. So assume everything is incoming, in which case we're calculating the amplitude of an E plus, E minus, and 2 photons, or more generally, some fermion bar, fermion gamma gamma. And what you want to do is you want to write down the Feynman diagrams that contribute to this, and just look at them, and you can see very, very quickly that some of them vanish and only certain things contribute. So one thing that you can convince yourself of very easily is that the 2 fermions need to have opposite helicities. That should be immediate. And that's not surprising, right? Because if we have, these are just electromagnetic interactions, so the helicity of the fermion should be conserved, or if they're incoming, they should be opposite helicities. But then the other thing that you can convince yourself is that if gamma, if the 2 photons have the same helicity, then the amplitude vanishes. Okay? So, and the reason it's so immediate in this formalism is that when we, remember that when we write down the polarizations, we have a polarization epsilon 3 and a polarization epsilon 4 for the 2 photons. We can choose to write them in terms of reference momenta. And if we make a clever choice of the reference momenta, we can see that many things go away. So in particular, you can see that the same helicity amplitude vanishes. And then you can also see what happens when the 2 photons have opposite helicities. Then we get something non-zero. And it's a very simple expression. So you should just go through the what I have in the notes here. And we'll see. Either we go over this today or tomorrow in the discussion, in the afternoon discussion. So this is just meant to be some practice for how to work with these things. Okay, so I now want to move on, and basically up to now we just introduced some notation, but now let's apply this. So any question before we go on? Yeah.
When we calculate complex calculation, should we consider all the variables?
Just tree level, of course.
Yeah,
Okay,
yeah,
I meant just tree level. Yeah, yeah.
We can consider the external process and feature process.
Yeah, we need to write down all the Feynman diagrams, right? So this is not using any fancy techniques. This is just Compton scattering via Feynman diagrams. Okay, so you have 2 diagrams that contribute. You do the usual thing that you always do. The only thing is that you now use these 2-component spinners, and you use the reference momenta, and your life gets much simpler.
What I want to ask you is, when we calculate this amplitude using the original method, I didn't need to consider this variable.
Okay, so the question is, what do you mean by on-shell methods? So on-shell methods, there are many methods, okay? Here, I just want you to do the usual Feynman diagram calculation, but the only thing that I want you to use from the whole arsenal of on-shell methods is the massless 2-component spinners that we used and the reference momenta for writing the polarization vectors. That's all.
Then you mean I don't need to consider the diagram?
You do need to, yeah, you just do the usual Feynman diagram calculation. You just write, yeah, okay? But when you have, in the usual Feynman diagram calculation, you will have to write these 2 polarizations. Yeah, yeah, yeah. Okay, so that's the exercise. And it's all written in the notes.
Yes.
Okay. Okay, very good. So now I want to, so in some sense, this is kind of, we haven't really talked about on-shell methods. We just introduced some notation, but now let's do something a little more powerful with on-shell methods, because essentially, as we promised, what the name of the game is going to be to construct amplitudes without referring to Lagrangians or Feynman diagrams and things like that. So we're going to start with massless amplitudes. And specifically, we're going to start with three points. And we're also going to see how the bootstrap program works. Okay. So the example that I showed you yesterday, or the example that I sort of advertised yesterday, is what happens when we look at the interactions of spin 1 massless particles. So the first thing I want to do is I want to look at the 3-point amplitude for 3 massless particles, spin 1. But these 3-point amplitudes are, in a way, very, very simple. We can get all of them together in one line. So let's do that. Now, they're simple, but they're also a little tricky. And the reason they're tricky is the following. So do you have can someone think about why they're tricky? So I'm thinking about 3-point amplitudes for massless particles. So they don't exist, right? As you say, they're kinematically forbidden. I cannot have one massless particle go to 2 other massless particles, okay? So you should throw me out of the room because I said I want to talk about on-shell amplitudes, and this is certainly not on-shell. And in fact, you know that if I have masses M1, M2, M3 here, I can only make this work if M1 is bigger than M2 plus M3, and I'll let you have the equal sign there too. Okay, so in a way, the thing that is really physical is massive amplitudes. Okay, so in some ways they're much simpler. And for massless particles, this is actually not allowed because we cannot have P1 plus P2 plus P3 equals 0 with Pi squared equals 0. And if you've never seen this, then you should convince yourself that this is really true. I mean, this doesn't work. So what's the solution? The solution is to go to complex momenta. If we go to complex momenta, we can satisfy all these equations. Okay, so this is why we will talk about complex momenta. Okay, now one thing I want to emphasize here, my convention is going to be always that everything is incoming. Okay, all my particles are going to be incoming. Okay, so let's see the same thing, or let's talk about what happens in terms of spinors. So we said our momenta needs to be complex. Good, so we go to complex momenta. But now let's write them in terms of massless spinors. Okay, so let's look, for example, to P1 plus P2 squared. So we said that this is equal to 2P1 dot P2. And we said that this is equal to 1, 2 times 2, 1. But on the other hand, it's also equal to P3 squared, and this guy is 0. So that tells us that either 1, 2 is 0 or 1, 2 square is 0. They can't be non-vanishing together. So let's suppose that 1, 2 is non-zero, and this guy vanishes. So at this point, we have 1, 2 equals 0. But I can also look at 2 times 1, 3. We said 1, 2 is 0. So this is 0. But this one I can write as minus 2, 1, 1, 3. But remember, this is just sort of P1 slash, right? So this is just equal to minus 2, 1, 3. Where what I mean by this is really P2, P1, P3. Okay, this is what it is. And now what do I want to do? Now I can say, let's use momentum conservation. And is that what I wanted to do? Yeah, okay. So why did I want to do this? I'm sorry. I didn't have a 0 here, right? I said that 1, 2 is non-zero. So we're just doing this manipulation. Now I can use momentum conservation. And 1 equals minus 2 plus 3. Okay, I just use momentum conservation. But now you see that I get 0 on this side too, because I have 2 plus here, 3, 3. And these are all massless spinors. So 2 acting on this side gives me 0 because of the Dirac equation. And 3 acting on this side gives me 0 because of the Dirac equation. So altogether, I get 0 here. So what we find, remember, is this guy was non-zero. So this guy here has to be 0 too. So we started with 1, 2 squared being 0. Now we find that 1, 3 squared is 0. And if we repeat the same manipulation, we'll also find that 2, 3 squared is 0. That is, all the squares are 0. So notice that this is completely general. We didn't assume anything about the spins of the particles. So for 3-point amplitudes, either all ij equals 0 and only ij survive, or the other way around. What does it mean that all of these guys vanish? It just means that all the square spinors are not independent. They're all sort of parallel to each other. Let me call them 1, 2, and 3. So 1 is proportional to 2, is proportional to 3. Okay? Or it's the other way around. So the 3 points live in either square spinor kinematics or angle spinor kinematics. Okay, so you see that they're very special. They can only be defined for complex momenta, and they either live in square spinor kinematics or angle spinor kinematics. So I can write my amplitudes either in terms of square spinors or in terms of angle spinors. So that's really, really nice, because now it means that these amplitudes have a very simple form, and we can actually determine all of them very easily just in terms of the external helicities. So let's see how that works. Okay, so let's say we have some massless amplitude, 3 point, and the external legs have, so this is P1 with helicity H1, this is P2 with helicity H2, and this is P3 with helicity H3. And so we know that the amplitude, let me use the labels 1H1, 2H2, 3H3. And I can write it as some constancy times 1, 2 to the power n1, 2, 1, 3 to the power n1, 3, 2, 3 to the power n2, 3. So that's one possibility. Or another possibility is that it's going to be equal to some C prime times 1, 2, let me call it N1, 2 bar, 1, 3, and 1, 3 bar, and so on and so forth. And we still don't know which one of these options is going to be realized. Is it going to be in terms of squares or in terms of brackets or in terms of angles? But we'll see very soon how it's going to be determined. Okay, so let's first of all look at scalars just as a warm-up. Okay, so how do I want to use this? So let me think about 3 scalars. 3 scalars means that H1, H2, and H3 are all 0. And that tells me that if I look at the helicity weight of, let's say, let's work with this form. Suppose I look at the weight of 1. I know that this 1 should not appear, okay? Because the scalar doesn't carry any polarization. So there shouldn't be any little group weight under 1 or 2 or 3. So altogether, N12, N13 needs to be 0. And similarly for 2, 2 shouldn't appear. So N12 plus N23 should be 0. And similarly for 3. So from this, we see that all the Nij should be 0. So for the scalar, we see immediately that the amplitude can just be a constant. Now, what can this constant be? So let's just do a dimensional analysis. So the dimension of this amplitude is 1, because remember that for an endpoint amplitude, its dimension equals 4 minus n in 4 dimensions. And if you don't remember why that's the case, then you should convince yourself that that's the case. Just go look at the formula for the cross-section, and you can see that that's the case. So anyway, in this case, the dimension of the amplitude, because it's a 3-point amplitude, so n equals 3, so its dimension is 1. But this was just a massless particle. So we don't have any mass scale in the problem. We don't have any scale that we can put here. So we see that this amplitude vanishes. So there's no 3-point amplitude that we can write for massless scalars. Okay? So that's, this is the first result that we got using real on-shell tools, okay? So it's a very simple result, but we're happy, okay? We found something that, of course, we could have found using Lagrangians too, but, you know, it's a nice exercise to convince yourself of that using Lagrangians. Okay, so now let's do the full story, not just for scalars. So in general, these equations will be modified as follows. For some arbitrary spins, n1 plus n12 plus n13, which counts the numbers that this one appears, for example, is equal to 2 times h1. Because remember, for a spin 1/2 particle with positive helicity, the helicity is plus 1/2. So we said that the weight should be 1 in that case. In other words, 1 should appear only once. Okay? So for spin 1/2, we get this 1 appear only once. If h1 is plus 1, so 1 is a vector, it should appear twice. So n12 plus n13 should be equal to 2, and so on and so forth. And similarly, you can write training equations. It's exactly the same. And we get the end result here. So let me just see. Let me just write it here. So what we find is that here we have h1 plus h2 minus h3. Here, this power is, you know, the permutation of that h1 plus h3 minus h2. And this one is h2 plus h3 minus h1. Okay, and so we have a closed form expression for all the 3-point amplitudes of any spins. And we could, of course, do exactly the same for this guy. And let me give you the result here. So this is just going to be the negative of that. So this is h3 minus h1 minus h2 times 1, 3 to h2 minus h1 minus h3, and so on and so forth. So now we're almost done. Because we still need to determine which one of these forms appears. And so remember, again, the dimension of this amplitude is 1. So we can see that the dimension of C has to be equal to 1 minus the sum of all the helicities, and the dimension of C prime has to be 1 plus the sum over all the helicities. And one thing that I used here is that ij has dimension 1. Okay, this is a super confusing notation, so we're not going to use that. So ij and ij are mesh dimension 1. Because remember, their product is equal to Sij, or we said that their absolute value is equal to the square root of Sij, and Sij is Pi plus Pj squared. So the square root is dimension 1. Okay. Yeah. Yeah.
My question is, what is N2 and N12 and N13? I think it is the power of the other.
So, and so remember, I just wrote down an ansatz, but I erased it already. So I wrote down. Okay, so I wrote this. We had this thing, right? N12, and then 1,3, and 1,3, and 2,3, and 2,3. These are n's, not h's. And so, for example, let's suppose that h1 is a half. So leg 1 is a spin 1/2 particle. Okay, so we know that the amplitude has to have one occurrence of this guy, this spinner, not more. Okay, so we're just counting that. Okay, on the other hand, if my h1 is 1, that is a vector, then I should have 2 of these guys up here. Okay, yeah, so this is all we're doing. Super naive. Okay. Good. Okay, so you see what's going on. So we have the dimension of C and we have the dimension of C prime. Now, C was just some coupling sitting in front of this kinematic structure. So if the dimension of C is negative, then it means that it's some non-renormalizable interaction. And if C is 0, it means that it's a renormalizable interaction. But if C is bigger than 0, we don't know what to do with it. Because again, there's no mass scale in the problem. So we can't get a coupling that's, that has some mass dimension, positive mass dimension here, if we're working with a local theory. Okay? So only this thing or this thing is allowed. And so that's going to tell us exactly whether it's this form or this form that the amplitude takes. So depending on the sum of the helicities, we know whether the amplitude is written in terms of square spinners or angle spinners. So for some of hi bigger than 1, the amplitude is written in terms of square spinners. Namely, we have that form over here. And if this is smaller than -1, we have angles. Okay, so that's the story. And there's another way that you can conclude the same thing, which is really sort of equivalent, which is to say, suppose that I take all my momenta. Let me take all my momenta and rescale them. So I want to write them as r times some xi, where this is dimensionless. Okay, then I can take them to 0 by taking r going to 0. And I want the amplitude to have a good limit when I take r to 0, right? I don't want the amplitude to blow up as I take all the momenta to 0, because that would mean if it blows up when I take all the momenta to 0, it means that I have some non-local interactions in the theory. Okay, so it's a sig theory. So by requiring that the amplitude goes to 0 as r goes to 0, this will tell us whether it's the formula that I marked with a star there or 2 stars. Okay, so that's the end of the story. We now determined all the 3-point massless amplitudes. Okay, that's the end of that story. Yeah.
Because there is no massive scale the problem, that there is no entry to the C rather than 0.
Yeah.
But maybe the first theory has another while external.
Yeah, but not the mass, right? So okay, good. So suppose there is some other mass scale, okay? For example, a cutoff or whatever. So the cutoff can only appear in the denominator. It cannot appear in the numerator. So that's all I'm using.
That's why you allow the first place.
Yeah. Right, exactly. And that's what we're going to see right now. Okay, good. So that's exactly what we're going to do. Okay, so now we can do the thing that we promised from the beginning and look at the 3-point for the vector particles. So we have 3-point for massless spin 1. And of course, it depends on the helicities. So here again is the 3-point, and we have 1, 2, 3, but now they're all spin 1s. And now let's imagine that they have the same helicity. So this is plus, and this is plus. So we can read off all the h's are 1 in this case. And so you see that it's the square and not the angle, because then these guys appear with positive powers. So in this case, m equals some c times 1, 2, 2, 3, 1, 3, 2, 3. And I can have some constant appearing here. But there's also, let me give them labels, A, B, and C. Because let's assume that I have a bunch of them, okay? A bunch of degenerate massless spin 1 particles. So I can also write here some C, A, B, C. Okay, so there are 3 C's in this equation, and they're all different. But I'm sure you can, you know, I'm sure you've seen worse in your life, so it's okay. So, okay, but you know what? Let's put some. No letter is good, so let me put a C tilde. Okay, so okay, so this guy I want to be dimensionless. And first of all, let's talk about the C here. So we said the amplitude, let's talk about dimensions. So the amplitude has dimension 1. This whole thing has dimension 3. So that means that this guy has dimension -2. So I can write this as 1 over some lambda squared, where lambda is some scale. So that's exactly what you asked me. So here I have a scale appearing, but it's appearing in the denominator. So that's consistent with being an unrenormalizable interaction. And there's nothing wrong with that. It's there. And there's another thing that we can say, which is kind of in the spirit of what we already said yesterday. So if you think about exchanging 1 and 2, this thing is anti-symmetric, but these two factors just get exchanged. So overall, I get a minus sign. And similarly for any other exchange. So if I look at the kinematic structures, at the kinematic structure, it's anti-symmetric under exchange of 1, 2, and 3. So that means that this guy is totally anti-symmetric in the indices A, B, C. Okay, so I learned that it's anti-symmetric. So it's consistent with being the structure constant of some Lie group, but it's actually, it corresponds to a non-renormalizable interaction. So it's not the gauge interaction that we're interested in. But what have we discovered? We discovered that the 3-point amplitude of massless spin 1 particles allows for such a non-renormalizable interaction. And this is precisely the non-renormalizable dimension 6 interaction of 3 gluons, which you can write as trace g cubed with 1 over lambda squared. So if I write it in the Lagrangian, this is 1 over lambda squared trace f mu nu, f mu rho. Okay, let me write g's here. G, G, and G. And the trace here is over color indices. And if I write this thing down explicitly, it's 1 over lambda squared FABC, GA mu mu, GB mu rho, GC rho mu. And it comes with an FABC. Okay, and you can convince yourself using Lagrangians that this is the only dimension 6 that you can write for Yang-Mills theory. There's also the one that's CP odd, but let's forget about that for a second. So this is it, and we just discovered it in this little exercise that we did here. We also see right away that it's proportional to the FABC because it's totally anti-symmetric, which tells you that you cannot write it for photons. Okay, you cannot write such a term with photons because this, you can convince yourself that for F mu nu, this thing vanishes identically. It's just really much easier to see it using these amplitudes. So you see right away that because we're constructing the amplitudes from scratch, we'll find both renormalizable and non-renormalizable interactions. We're finding the completely general amplitude. So of course, we'll also find the EFT amplitudes. Okay, but now let's talk about the more interesting thing, which is the gauge interaction. So the gauge interaction has to come with a renormalizable coupling. And so what else can we do here? We can, of course, we can take all the helicities to be minus, in which case all the squares will be replaced by angles. Or we can replace 1 plus with a minus or vice versa. So let me change this one to a minus and this one also to a minus. And in this case, our M is now, let me call it C prime times 2, 3 cubed divided by 1, 2, 1, 3. And let me call this again CABC. Although in principle, I could have called it with a prime, but never mind that. So again, this is dimensionless. And now, again, whether it's angles or squares is dictated by the rule that we had above. And you see that it's always the one where these spinor structures appear in a positive power overall. Okay. So now again, I can look, first of all, let's look at the dimensions. So this is dimension 1. This also is dimension 1. And so this is dimension 0. So this is consistent with being the gauge interaction. And looking at the exchange, suppose we exchange 2 and 3, for example, then this guy picks a minus sign. These two just get exchanged. So again, it's totally anti-symmetric in these guys. And so we learn that this also is fully anti-symmetric. So again, this is like the structure constant of some gauge group. And in particular, we learned that the index A has to run over 3 over n that's larger or equal to 3. Okay? If we just have a single guy, which is going to be like a photon, this interaction doesn't exist. We don't have a self-coupling of massless spin 1 particles. In the case of photons, this is known as Ferri's theorem, right? I think you've all seen that. And it's true in general for n, for n which is odd and is related to charge conjugation. And the minimal number of self-interacting spin 1 particles that we need is 3. And that's exactly what we have in the standard model. We have the W plus minus and the Z, which form 3 guys. And if I go to the high energy limit, these amplitudes look massless, and we're recovering the SU2 structure. Okay, so the smallest group that we can have here is SU2. Okay, so that's what we said we will see, and we're really starting to see here the structure of Lie groups at the level of the 3 points. Okay. Good. A few more comments about this. First of all, I can do exactly the same exercise, and I will do exactly the same exercise for massive degenerate spin 1s, and we'll get the same result. And as we already said, we see the structure constants here, or all we know at this point is that these are consistent with being the structure constants, but in order to really see that, we have to look at the 4 point. So that's almost the next thing that we'll do. But before we go there, let me talk about another amplitude of interest, which is something that we care about a lot, and that's the interaction of fermions with a spin 1. So let me look at a fermion, and a vector. So this is something like this. And let me choose, for example, for the helicities 1 plus 2 minus 3 plus. Okay, so this is going to be 1, 2, and 3. My vector is going to be the 3. And so in this case, the sum of our helicities is 1/2 minus 1 plus 1/2, which is 0. So actually, no, sorry, this was minus 1/2 plus 1. So that's 1. which is bigger than 0. So that tells me that I have to live in square kinematics. And the amplitude in this case has to be some c times 1, 3 squared divided by 1, 2. And again, looking at the dimensions, this is dimension 1, this is dimension 1, so this is dimension 0. So it's consistent with being the gauge coupling, okay? It's dimensionless. And one thing that you can do, which is a nice exercise, is just to convince yourself that that's the case. Just take the Feynman rule for the interaction vertex of these guys, dot it with the polarizations. Of course, you have to assume that all the momenta are complex, and you can convince yourself that this is the form of the amplitude. Now, of course, one thing, okay, let's say a little more about this. I mean, let's suppose that I have more than a single fermion species and more than a single vector, so I can put indices on these guys. So this one is I, this one is J, and this one is A. So here I have some C, I, J, A that would appear. And the thing that I would want to see is that the relations that I expect for the gauge theory hold. That is that this coupling here is the same as the gauge coupling, and this structure here is the same as TAIJ. And in order to do that, you have to look at 4 points. So in this case, you'll have to look at things that involve 2 fermions and 2 gauge bosons, for example, and you'll be able to convince yourselves of that. Okay, so you can play all of these games. Okay, so at this point, we know everything we want to know about the 3 points, and we can just move to talk about the 4 points. And in terms of the bootstrap, what we've done here is we have all the 3-point amplitudes, and now we need to go to higher ends. And essentially, the thing that we'll need is we'll use how these amplitudes factorize on the 3 points. Okay, so for now, everything I'm going to say is going to be at tree level. So I'm interested in looking at some amplitude A, and we said before that this is a function of the polarizations and what I'm going to call the Lorentz invariant. And I'm putting this in quotes because what I mean here is it can be something like Sij, which is Pi plus Pj squared, but also I want to include here things like P1 plus P2 plus P3 squared or any other thing like that. So I'm talking about 3 amplitudes for some higher n, even beyond 4. Now, the polarizations, we know how to write them in terms of spinor products like this. And I can label them collectively as Ij in parentheses. So the parentheses can be either square or angle. And what I know is that because I'm working at tree level, this A has to be a rational function of the Sij and also these guys. So this is something that we're going to use very heavily. And then there's another thing that we know. we know what the analytic properties of this amplitude are. So we know that it should only have single particle poles. And these single particle poles correspond to some pi plus pk squared going to 0. Right? So all the poles of this amplitude are going to come from stuff like this, where here I have some, well, let me also write something like this. In any case, I have one propagator that goes on shell. So these are the only poles of the amplitude. And I also know that the residue of the pole should be equal to the product of the amplitude that sits here and the amplitude that sits here. So let me call the momentum that's flowing here P. So the residue has to be equal up to some factor to the amplitude on the left, 1, 2 to P, times the amplitude on the right, minus P, and let me call it K to N, whatever these are. But the residue is equal to this amplitude times this amplitude. Okay, is this clear? Now, if I have an analytic function and I know all the poles, then I know the function, right? I mean, the function is completely determined by its poles, except for this little thing that we worry about if we're mathematicians, which is how the amplitude behaves at infinity, right? So in order to infer the amplitude from its behavior near the poles, I also need to assume that it's well behaved at infinity. Otherwise, what's the problem? The problem is that in playing all these games, what you do is you want to use Cauchy's theorem. So you have a function, and the function has these different poles in the plane, and now I want to use Cauchy's theorem, but I need to deform some contour going around here into other contours, and then I have to also know what's going on here, whether I can neglect the integral at infinity. So this is actually, I'm kind of taking this very lightly, but it's going to be super important for us because, what determines the behavior of the amplitude at infinity, roughly speaking, is if it's a renormalizable amplitude, everything usually goes to 0 fast enough, and we can neglect this amplitude, we can neglect this integral at infinity. However, if we have a non-renormalizable interaction, then we have contributions to the amplitude that grow with the momentum, and then it may not be well defined at infinity. Okay, so that's something to keep in mind. But as we'll see, it doesn't really stop us from inferring the form of the amplitude, because we just have to know whether we're trying to extract something that's renormalizable or trying to extract something that's non-renormalizable, and so on and so forth. And there are also some ways for defining this integral at infinity such that it vanishes even for non-renormalizable contributions. Okay, so I guess I have to stop in 5 minutes. Somehow I thought I still have another 30 minutes, but that's not quite correct. Okay, so let me see. So let me just finish this story, which is not going to take very long. Okay, and so what's going to be the plan at this point? So the story is essentially, the story is very simple. We have an analytic function. We know what the poles are. We know the residues, so we can infer the function. So how is this going to work? Well, we already know all the 3 points. Now we can determine the 4 points. Once we know all the 4 points, we can determine the 5 points, and so on and so forth. And this is the bootstrap. Okay, when people say bootstrap, this is essentially what they mean. Now, of course, this is very simple in theory, but it's not so simple in practice, because these are not functions in a single complex variable, right? There are functions in many complex variables. There are functions in all these SIJs and also the spinor products. So very often, what people do, or one of the big, okay, let me say something. In some cases, you can still work sort of brute force, and we're going to do some brute force calculation. Namely, we're going to use these properties of the amplitudes and be able to infer the amplitude just from lower point amplitudes. And this is something that people have done even something like 30 years ago in the 90s. Byrne and Dixon and Kosower applied this very, very successfully to guess the form of QCD amplitudes, and not just 3 amplitudes, but 1 loop amplitudes. And they got very, very complicated amplitudes using these methods. But one piece of progress that was made in the early 2000s is what's called recursion relations using shifts, where the idea is to take this problem and convert it into a problem in terms of a single complex variable. And then you can apply Cauchy's theorem and all the machinery to this function of a single variable. So this is something that we're going to sketch. We'll see how much time we have to talk about it, but at least I'll give you the main idea. But the next thing that I want to do is I want to apply this completely brute force to the case of 4-point gluon amplitudes. So this is the next thing that we're going to do. So we're going to look at a 4-point that involves 4 spin-1 massless particles. And so this is going to be 1 with some index A, 2 with an index B, 3 with an index C, and D, and 4 with an index D. And we're going to try to construct this one from the 3 points. And this is how we're going to find the Jacobi identity. So this is what we're going to do tomorrow. Okay? So any questions before we finish?